Thank you. So good morning, good afternoon, good evening, depending where you are. And first, thank you so much to everyone to join this webinar. It's always difficult to find a great schedule for everybody around the world to participate, but we are recording and the session will be available soon for those who cannot attend, like to be present today. And I'm giving a brief introduction to this webinar. Also on behalf of my co-hosts, Sofia Bath from the University of Porto in Portugal, Agnes Bari and Flavia Finito from the McGill University in Canada, and also with the support from the GEO BON Secretariat. So this webinar has been organized as part of the strategic plan of the GEO BON Ecosystem Services Working Group. And we want to contribute and support global monitoring of essential ecosystem services variables and those dimensions that come with the ecosystem services and biodiversity. So we are organizing this webinar around discussing strategies to address interoperability of ecosystem services data, models, and software. Because while the literature around ecosystem services continues to grow rapidly, knowledge from this body of evidence is rarely reused in an efficient and comprehensive way due to the limited state of interoperability of ecosystem services. So we have challenged three different people here with three different backgrounds. So Ken Backstad works at the United States Geological Survey, coordinating the activities on natural capital accounting. And he is also an expert on data interoperability for ecosystem services. And this is shown by his work in the Artificial Intelligence for Ecosystem Services, the IPBES project, and with the UN to develop the IPBES for SEEA application and the SEEA interoperability strategy. Our second speaker is Flavia Finito and works on methods and approaches to monitor ecosystem services in Canada. His work focuses on understanding change in social ecological systems to guide reporting, policy, and actions. And our third speaker is Jean-Michel Lord, who is developer and Scrum Master for GEO BON. And he has coordinated the new developments of BON in a Box, as well as developed the supporting web platform. And in the context of the BON in a Box, interoperability has been a critical topic to facilitate developments from various labs to work together in shared indicator pipelines. So Ken will start the webinar with an introduction on interoperability in ecosystem services. Then Flavio will show us the role and needs for interoperability in GEO BON. And finally, Jean-Michel will talk about advancing interoperability for BON in a Box. We also invite everyone to place the questions or comments on specific topics that the speakers are presenting today in the Q&A, and we will be thrilled to answer after the presentation. And then, Ken, the floor is yours. You can start.
Thanks so much, Nuria. Is everyone seeing my screen okay? Wonderful. Well, I'm going to lead us off with a discussion of what interoperability is and why it's important. Thank you so much for the introduction and the invitation to speak today. And I'm leading off here with an image of one of my favorite elements of biodiversity, the North American bison. So I also want to lead off with acknowledgements, and particularly a number of co-authors who have helped in work on a recent thought piece on this, which is currently in review at Ecosystem Services. I will certainly be excited to share this when it's published, but in particular, some of the folks noted below who were instrumental in getting some of these ideas together and bringing a diverse perspective that incorporates major international initiatives related to ecosystem services, GEO BON, IPBES, and SEEA, and I'll be talking about some of that today. So first, why does interoperability matter? We all know we live in the age of big data. There is an ever-increasing, sometimes the word exponential is thrown around. I'm not sure if that actually is true, but we know this is a vastly fast growing space, both in terms of the amount of data shown in this bar graph at the bottom, and in terms of the amount of research. This is journal articles using the term modeling that show up in the journal Ecosystem Services. And that's one journal, of course, showing close to 1,300 results. So how do we integrate and make all this diverse data and models work together to the advantage of these important international initiatives? That's what I'll be talking about today. Now, the state of the art, unfortunately, is for a relatively low level of reusability. This is perhaps an old school version before we had widespread use of the cloud, but for many years, and in many places still, this is still the norm, with quite a lot of time and money being spent to process data, to understand the literature and bring together the best models. And at the end of the day, hopefully that is put into a data repository, but we know that even isn't always the case. And even a data repository isn't always fully interoperable, as I'll get to in a moment. So what happens when our science isn't reusable? There's a nice overview article talking about what happens. Basically, we can't all, the literature is growing so fast that no one person and no one research group even can keep up with everything that's happening. We all have that feeling, I think, when we do research. So we're not reusing data. In other words, expensive and high quality research isn't reused. The state of data sharing isn't great. This is often better among younger generations of scientists, so this is moving in the right direction, but it's not uniform. Data sharing isn't always prioritized. As a result, our ecosystem service assessments are time-consuming, incomplete, and have less real-world impact than they should. And I feel strongly that this is a global equity issue. Particularly scientists from the global north have an advantage in better access to data and models. And so I often work in the SEEA space and think about the role of Global South National Statistical Offices, but that holds true for any sort of ecosystem service assessment or perhaps BON in a box effort being compiled in the Global South. There's a higher bar for it because the tools, the data, and the models are less accessible. And that's not in my mind, an acceptable status quo. And that status quo is a problem. I like this quote. Einstein may or may not have actually said it, but if we think that the same thing is going to get us there, that's probably not true, and I'm doubtful of that myself. So a solution to this is something called the FAIR principles. Many of you are probably familiar with this, the idea that data models and science in general should be findable, accessible, interoperable, and reusable. The first two and the last are fairly self-explanatory there. I'll explain interoperability. There was a nice webinar from a few years ago by Data One, which is a federation of over 40 data repositories, looking at the state of play for findability, accessibility, interoperability, and reusability among their data. And what they found is that generally, existing scientific repositories for data and code are pretty good at making data findable and accessible. You can go out and search for things and find them. Reusability and interoperability lag substantially, and none of these have improved with time. So we really need perhaps new strategies to address the interoperability and reusability problem. So what is interoperability? A short definition is the ability of independent data tools to work together with minimal effort. And I would say it's a core challenge for modern science, given the speed that science is growing and the pressing need to address today's sustainability challenges. And because there's an implied ability to work together with minimal effort, that doesn't just mean data, that means computational pipelines too. There's a nice paper from 1995 that although it's old, I think is still very timely in defining interoperability. There are multiple definitions out there, but a useful one is that there's a distinction between what's called syntactic interoperability. So let's just use compatible data formats and communication protocols, APIs and such, and data standards. And that's good. That's definitely an important step beyond the status quo. but a higher level bar that we've been working toward on the Aries project and trying to raise awareness in the scientific community and build excitement around is semantic interoperability, where a receiving computer system can actually interpret the meaning of the data that it's ingesting and reuse it appropriately. That's, as you would expect, more complex, but there's better potential for automation and improved data and model reuse. So there are good reasons to pursue it. And I would argue that the community is starting to think about this a little bit, or parts of the community at least. I think much of that activity has come from Europe. I'll call out in particular this Blueprint article that happened in 2013 and this visualization tool article that happened in 2015. Both of these were really important. They were looking at building consistent metadata for ecosystem service studies and at taking ecosystem service maps in particular, making them more fair, even though 2015 was before the FAIR principles were in use. That was really what these were trying to do. There are various reasons why I don't think these have caught on that I'll get into later, but I think it's a really important starting point to acknowledge that people have thought about this, and it needs perhaps a renewed focus. And I'll talk a bit as well about semantics, the words we use to describe metadata for our data and models. And I would argue that we spend a lot of time arguing about consistent definitions for ecosystem services. These are a few of the terms that you see both for ecosystem services themselves on the right and for some of the relevant terms defining ecosystem services. So there's been a lot of literature talking about these, advocating for a particular view or a particular set of terms, but much less time talking about consistent labeling for data and models, which is the space that we're working in this paper that I mentioned that's currently in review focuses on. So again, how to improve the status quo. What we are working toward is, instead of the status quo on the left here, is a world where, because experts have contributed their data, models, and their knowledge about when, where, and how to reuse data and models, and put it on the web in a way that a computer can use and interpret, that makes the job of the person here on the left who has a question about ecosystem services much, much faster and cheaper, which brings all of our work into wider use, which is, of course, very important. So what might this look like? In any case, even a very experienced modeler, let's imagine a hydrologic modeler who's approached with a particular problem, knows some particular models, knows of some data sets. They have familiarity with some subset of the scientific literature. But of course, in today's world, especially, they certainly don't know it all. If we had a global commons of interoperable scientific data and models at various scales that this modeler could tap into, then they would immediately be empowered to do more work. They might still choose one of their data sets or models, but they would have others at their disposal that they would be able to peruse, understand the limitations of, and integrate where appropriate. Better yet, if they can take their own knowledge and make it interoperable in a global commons, now the global commons itself becomes more powerful and complete. If they have a tool like Aries to support the integration of that science, to generate maps, results, and the provenance or the information about where these data and model choices came from, which is very important in an automated system, then they can really start doing some excellent work quickly. And ideally, they can iterate and update that model periodically as new data become available because of the automation aspect. So you can see where this is going. This is very different from today's world of downloading data, integrating it into a model, extensively testing that model, and by automating that. And it's an arguably much more powerful vision for the future. Importantly, countries also do this. Again, I come from mainly the world of SEEA accounting, where countries are thinking about which accounts are they going to compile, which data and models are they going to use. They're testing, validating, and publishing accounts, and they're doing periodic reassessments. If there's an additional step here where countries are making data interoperable and including the available global data and contributing global data where appropriate, then we believe that countries can more quickly compile accounts, not just within country A, but within all countries. And this is the work we've been working toward in ARES for SEEA with the UN, recognizing that countries will have different contributions and different needs for a global data commons. Some countries may rely heavily on it. Some countries may be able to contribute strongly to it. But either way, whether this is SEEA accounting or some other aspects of ecosystem service assessment, with a global data and model commons, much more becomes possible globally. This is important because, of course, there are ambitious global monitoring targets that the international community has agreed to. I would argue that the status quo for the production, use, and institutionalization of ecosystem services is certainly progressing. We could argue about the slope of this curve. And I would argue that it will improve under the status quo as familiarity improves, as other tools improve. But I believe that with a coordinated global focus on interoperability, we could get to these critical goals more quickly, and that's worth all of our time. What's interesting about, I believe, about IPBES, GEO BON, SEEA, and their support of the CBD and other global conventions is that there's a shared goal of continuously updated near real-time monitoring. And Flavio and Jean-Michel are going to talk more about this in the GEO BON context, but that has common needs. We need to integrate a complex body of knowledge, and we need to vastly improve the efficiency of that reuse. In other words, through automation to develop trusted, high quality, and rapidly turned around monitoring. What do we actually need for interoperability? I would argue we need more consensus on the need. The understanding about interoperability, I think, remains low, although it's better, certainly better than it was a few years ago. We need platform agnostic and machine actionable data and models. In other words, we don't sign up to a specific modeling worldview, or model, but we are able to use a variety of data and models for a variety of different problems. That requires us to use consistent metadata descriptors. Here's this term semantics again that I'll get into more in a moment, that can be navigated by AI to assemble models. And we need to pay attention to hidden costs. And there's an article that we published a few years ago here that gets into some of these issues. So I mentioned semantics. That's a very simple and simplified way to think about that is standardized metadata descriptors that a computer can understand and interpret and know what it's looking at. Open linked data. There are various requirements for that I won't get into here, but that we could talk about in the questions if people are interested in. Open linked models that again go beyond a standard code repository and add that machine actionability component. And importantly, guidelines on when, where, and how data and models should be reused. And with a few simple guidelines, we can bring that artificial intelligence aspect, and a computer system can know when is it most appropriate to use a particular data set or a particular model. If anyone's interested in semantics, this is the one slide I'm going to spend getting a little bit more into it. And what I find interesting is that there are 4 journal articles that were independently produced that basically advocate for the same solution. So my image there is of convergent evolution on the right for flight in animals. And if you have multiple groups proposing the same solution, it might be a really robust one and one to pay attention to. But essentially, when we're describing a particular data set or the outputs or inputs of a model, we don't want to use a really complex single term. We want to use small atomic concepts that we can assemble into more complex concepts. That keeps semantics simple. We want to measure both the phenomenon and the property being measured. Both of those are needed. So we wouldn't just talk about temperature, but we would talk about, for instance, land surface temperature in degrees Celsius. There are optional roles here for where a measurement occurred, the role of particular elements, and the measurement methods. There's a need for what's called a core or upper ontology that connects the knowledge of multiple scientific domains, ecology, hydrology, economics, sociology, et cetera, all the things that are connected to ecosystem services. And we want to reuse existing semantics and not reinvent the wheel. I mentioned the idea of being more agnostic about models. I think oftentimes we reach for a particular model, and I'm guilty of this myself. I'll point to this article of my own in 2013 that sort of evaluated the very early ecosystem service model landscape. And I think we need to think more about which model is better for my problem and not just grabbing a particular model to solve every problem. The useful phrase to remember, which is a classic in modeling, of course, is that all models are wrong, but some are useful. So which model is most appropriate for my problem of interest? So when do we use different models? Is it different models or parameterizations or data sets that are most suitable for a particular ecoregion, spatiotemporal scale, or for when certain data are available, to make them and their data open and interoperable so that AI can navigate that complexity and use it together? Importantly, interoperability solutions need to be trusted, user-friendly, equitable, and community endorsed. My colleagues and I on the Aries team have done a lot of work on the technical aspects of interoperability for ecosystem services. But equally, or perhaps even more important, this blog post on the right is one that I really like, and I point people to because it talks about the role of people. Obviously, there's a strong human element here, and we need these dimensions of trust, user friendliness, equity, and community endorsement if interoperability efforts are going to be successful. So who should be behind ecosystem services, behind ecosystem service interoperability? I would argue that ultimately this does need to be the researchers. We need to make this part of institutional culture. We also need to provide the tools that make this easy enough to do. So it's not yet another thing a researcher has to do at the end of their already busy workday. And again, I'll bring up these two articles that I mentioned earlier, which I think really were ahead of their time and pointing to the need for documentation and even an early view of FAIR in the ecosystem services community. And, I think particularly with these global initiatives like GEO BON, IPBES, and SEEA, perhaps those could provide the coordinating mechanism for a renewed push here where some of these initiatives failed or haven't yet achieved success. We need as a global community to step up and to find ways to make this happen. And there are huge benefits, I would argue, for the global south and for the integration of ecosystem services and decision-making everywhere, both in the global south and in the global north. Getting a shared vision is important here, and this 2023 interoperability strategy, which you can find on the UN and the BC3 websites, points to a view for SEEA, but I think it's relevant for all other parts of the community too. We talk about being able to rapidly recompile work as new science emerges, quickly reproduce results to show the most recent trends as new data become available, and to make strong international comparisons, but also to relatively easily customize the assessments and accounts for specific countries wherever we can do that, all with the goal of moving the information more quickly into the hands of decision makers, the public, and the media. I think this is a shared goal, but I'd be interested to hear perspectives if you have other views. And one example of where we're making that happen, which is exciting, is a European Space Agency funded project between the Aries team at the Basque Center for Climate Change, VITO, which is a research institute in Belgium, and the ESA to integrate the Inca models, which are the European Union's accepted ecosystem service models for the purpose of natural capital accounting, integrating them with the European Space Agency's OpenEO platform and with Aries, which provides the semantic front end to assemble the best available workflows for a problem of interest. So this is some exciting work that's going to be presented at the 2024 European Ecosystem Services Partnership Conference, among other places, to try to integrate some of these efforts, bring them together with big data and semantics and AI to improve their fairness. I'll start to close by pointing out a few caveats to this work. First of all, I think it's interesting and important that we've seen the word ontology used increasingly in the ecosystem service literature in the last few years. And this is often in the case of talking about understandings of reality and talking about nature's contributions to people, indigenous worldviews, et cetera, talking about the idea that there truly are different ways that humans can understand their worldview. And the Western materialist worldview is one of those, and indigenous worldviews are another. And these need to coexist in the ecosystem services space. And in particular, the indigenous worldviews are very important to elevate for a variety of reasons. But that term is not the same as the one that we talk about in this article and that I've been talking about today. And the way that I've been using it is basically, as I've said, systematic descriptions of concepts, entities, and the relationships between them that are consistent and descriptive. And if we make the first example, if we promote pluralistic ontologies in the first case, that basically means that indigenous worldviews ought to coexist alongside Western materialist ones, which I think many ecosystem services practitioners would agree with. On the second one, if we have pluralistic ontologies, if we have many different systems for understanding and describing our data and models, that will actually undermine our ability to produce fair science. So I would argue that we need pluralistic ontologies here, and we need a shared ontology in the second case for the ecosystem services space. I've mainly been thinking in the space of quantitative models and data, and there's a lot of qualitative data out there from the social science world, and it's very important, including indigenous data. So I don't want to minimize the importance of that or to suggest that we have easy ways to shoehorn that data into easy, fair descriptors. So I think that's an important thing to keep in mind. Much of what I've talked about is for now centered in the quantitative data and modeling space, and not the qualitative social science space, which is an extremely important complement in the ecosystem services field. And finally, getting at this a bit further, FAIR alone isn't a panacea. In particular, for indigenous data, there's the idea of the CARE principles, which are extremely important. And with data repositories, there's the idea of trust, which is another set of principles. So there are folks that are talking about the idea of FAIR plus CARE plus trust as being our best solution for addressing these diverse modern data management challenges. What needs to change? Our article does talk about roles for individuals, research groups, and institutions. And briefly, this figure is from our 2022 article by Balbi et al. In Environmental Evidence, and talks about the role of funders, scientists, practitioners, data and code repositories, and knowledge engineers. These are the people who help design and build ontologies and semantics and the tools to make them accessible. So all of these things need to work together. And my last slide here is, what can you do? First of all, learn more about interoperability and share this with colleagues. I believe this is an important first step as for us all to understand why it's important and to build our shared state of knowledge about interoperability. Practice the best open science practices you can. You don't need to immediately get to the machine actionability and the high-level semantics. Even starting with getting your data onto public code and data repositories is an important first step, and then continue to improve as you gain practice. And this goes not just for individuals, of course, but for research groups. We don't need fairness isn't a black and white issue where something's either fair or not fair. It's a shades of gray issue. So even if we're improving on fair incrementally, that's still important, and that's still very valuable. Look for a lead in your organization who can engage in this. So perhaps a data manager or a data steward, or just someone who's passionate about these issues. Not everyone needs to do this. Not everyone needs to be the expert. But if you have someone in your organization who can engage on this, that would be extremely valuable. And finally, connect with others who are interested in this topic and start to build upon and bridge existing efforts rather than creating new ones. So I think these are some concrete steps we can all take. Thank you again for your time, and I'm happy to answer any questions and to turn it over to the next speaker.
Thank you so much, Ken. I believe one of the sentences that you mentioned, like key ones, is like people are essential in data interoperability, and you show us like throughout your presentation. And we can talk more about that in the questions. Thank you. Flavio, now it's your turn. So the screen is yours.
Thank you, Nuria. Thank you, Ken. I'm going to say a few words building on some of what Ken has shared about why we need this interoperability and what it looks like within GEO BON and what it can make possible as we move towards a world that is trying to respond to the calls of the Global Biodiversity Framework. So this Global Biodiversity Framework that we've signed has now committed 196 parties to essentially reporting on progress towards the 4 goals that would allow us to live in harmony with nature by 2050, and the 23 targets that are supposed to bend the curve of biodiversity loss by 2030. And what's really exciting and a good opportunity about this Global Biodiversity Framework is that it comes with a monitoring framework where essentially all of these parties are expected to submit a set of indicators to the UN to track progress towards these goals or targets. And right now, we've got a lot of indicators available. Most of them have been negotiated, and some of them are optional, some of them are required. But there is a big need from parties for some capacity support. Some of these indicators are very advanced, others not as much, especially when we think about ecosystem services. Those are indicators to do with Goal B and Target 11, and they've come a long way, but there's still some work to be done. And more than work to be done, there's a lot of need from parties for capacity support. And that means that there's a really key role for the research community to fill here to support this implementation and move along on the reporting side of things. And specifically, this fits well with GEO BON's vision, which in the long term is looking to build a globally connected biodiversity observation and monitoring network that would allow us to share tools and data to provide support in the conservation management and sustainable use of biodiversity from local to global levels. And GEO BON has been working on this idea for a few years now, and it's in the process of developing it in collaboration with multiple partners, and mostly what we call national biodiversity observation networks. Now, how this might look like in the future is through a step-by-step process where from the ground up, people are engaged in their nations, that's stakeholders, that's governments, that's NGOs. Here you have an example which represents Colombia, where we look at the 4 steps of building a biodiversity observation network through engagement with people, the assessment of needs, the design of what the biodiversity observation network looks like, and then the implementation of this network. And what you'll see here in the middle is a nice graphical representation of essentially the reality on the ground of what is needed for biodiversity observation network. So we've got observations, remote sensing, eDNA, camera traps, really anything that we use to observe biodiversity and ecosystem services that then need to turn into these, go into these analytics pipelines that are responding to the network's needs, responding to the government's needs, and allowing us to compile these indicators that are relevant nationally and also globally to understand ecosystem service change and biodiversity change. And the goal this in the long term is to connect these through biodiversity observation networks around the globe in a system that would be able, as Ken presented earlier, to share information across biodiversity observation networks to get a good sense of how ecosystem services and biodiversity are changing and respond to the need of the Global Biodiversity Framework. What you see here in the bottom right is GEO BON's approach that relies on what we call essential biodiversity variables or essential ecosystem service variables to produce this change through some sort of standard format that we can integrate across countries and across systems. So just a few words on essential variables. They come from the space systems, where essentially what they are supposed to be is variables that are critical for observing and monitoring a given facet of the Earth system. Now, these variables, they don't just exist on their own. They come at the interaction of a few things. They need to be obviously there out in nature for us to measure, but also they need to be both relevant to what we're trying to understand, feasible to measure, and cost effective. And there at the intersection of these, we get these essential variables that we should be able to monitor and compile within these biodiversity observation networks at the local scale. And the change in these biodiversity observation networks, the change in these essential variables is what helps us understand how biodiversity and ecosystem services are changing worldwide. So we've got a few already that exist in the ocean science, in the climate science, and in biodiversity research. But when it comes to ecosystem services, they have been published in 2022, but there's still a lot of work to operationalize and design these essential variables, which is part of what we're doing here in the Ecosystem Services Working Group. And why we need these is because if we zoom back out and think about how we go from the data all the way to the outcomes of the Global Biodiversity Framework, is that within these national biodiversity observation networks, connected to a global biodiversity network is where we can produce the data needed to inform us on change. But really where we need a lot of interoperability and a lot more effort to build tools and pipelines that allow us to understand change is within the space of monitoring science. And this will only be possible if we build some of these semantically integrated pipelines that Ken was talking about, and if the academic community engages fully both with the data services, so those who produce the data synthesized from observations, and the knowledge services, those who work to produce the indicators that would allow us to track progress and action for nations to be able to plan and prioritize. This is the national level planning prioritization, but you can imagine that this can also be done at the local level and the global level. Because at the end of the day, these national reporting systems need to go back to the United Nations Convention on Biological Diversity and report their progress through the indicators for us to understand whether or not we've made any progress towards the goals and targets of the Global Biodiversity Framework. So I hope that in a few words here, I've showed you how interoperability is really key and essential for us to deliver on this grand vision of a globally connected biodiversity observation system that allows us to feed through integrated pipelines that produce these indicators that are able to guide decision and action. Thanks a lot for listening, and I will pass the word on to the next speaker.
Thank you so much, Flavio. And it's so important, right, interoperability for essential ecosystem services variables to inform about ecosystem change and global change. And now, Jean-Michel, the floor is yours.
Thank you. Thank you very much to Nuria and also Flavio and Ken. I've been really happy to hear you, Ken. Many of the things you were speaking about have been discussed also here in Quebec. Bon in a Box is a collaboration of many Quebec universities, as well as Quebec Center for Biodiversity Science and Humboldt Institute in Colombia. And yeah, I've been hearing many things that are in the air also on our side. I decided to rename this presentation Pipeline Engine Interoperability Within. It's a reference to a movie a few years ago. But I think it's important that to Bon in a Box, to have this interoperability as a built-in, not just a feature, but an essential founding principle. So what is Bon in a Box? It has a tool, search engine. It has a project search engine, which are more a classical repository of things that you can look for and that can be indexed by search engines. A note on the projects, by the way, the goal there is to make the projects that might be invisible to the web, to make them visible to the web. Many small projects in Colombia, for example, were added. And it's based on the ODIS architecture, which is a good example of interoperability as well. We have simply hooked on their existing framework, and we have our project repository there, and we can share back GEO BON's project. Everything that is coastal, we share them back to ODIS and the Ocean Info Hub search portal. But what I'm really going to focus on today is the indicator and EVV pipelines. It's this repository of model, well, one of the repository of models that Ken was hinting at. We're not hosting data. We're hosting models that can be built and assembled together to consume data and transform it into a valuable output, may it be EBVs or indicators. So what we want in the end is something like this, a nice dashboard. This is the Bon-in-a-Box result viewer, we call it. It's a nice dashboard. You see on it the final result, but also the key steps that the researcher has identified, so that the result is not only the end result, but that you can trust the process behind it. But this is still very high level for the decision maker. And this is what you want in the end. But in order to get there, in order to get to this, we need to make a lot of things work together. And all these things are pipelines that are behind the scenes. What a pipeline is a series of steps. Each step does an operation that transforms an input into an output that has just a bit more value than the input it had. For example, cleaning GBIF data is a really common example to say, okay, there are observations that are in lab locations and stuff like that. Clean them, and this step here is a step that has value not just in the context of pipeline A, but also in the context of pipeline B, C, D, E. Hence, this step, if it's conceived to be interoperable, it will be able to be used in many different processing pipelines. Now, assuming this pipeline is interoperable, you could get data in Python, you could transform data in R, and you can run a model in Julia. Different programming languages, but as long as they speak a common language in the middle, this is feasible. And this is what we do. The pipelines can be viewed, edited, and ran through Bon-in-a-Box, and this is something really relevant when new science comes in. Ken was speaking of new science and the ability to accommodate it really fast. Well, we can reuse whatever has been done by researcher who created model A and put model B at the end and keep the rest of the pipeline. And then we have interesting decisions like, should I use pipeline A or pipeline B? And this is where this AI for deciding which good pipeline or just solid documentation to understand which pipeline is better in which cases, like Ken was hinting at, becomes relevant. And something we could do also, since this is interoperable, well, why not put some consensus block? Because the output of A and the output of B, if there are, let's say it's two pipelines that do connectivity, but in a different way, then we could do a consensus block or some other operation on the outputs of these. But until now, I have just been assuming it's interoperable. I haven't been telling you how it is interoperable. So Ken showed syntactic and semantic interoperability. So within a pipeline, this is clearly syntactic interoperability. We are relying on files which have their standards in order to communicate between the steps. So you get the data, you create a CSV. You transform the data, you output another CSV, which happens to be in the same standard format than the CSV you got data from. Model A could run directly using the CSV from the get data step, or it could run with the CSV coming from the transform data step. This allows a third lab to come in and add another data transform step in between, click run the pipeline again, and see what happens with this newly modified pipeline. And pipelines can also run remote tools. So model B could be an API call to Galaxy for Ecology, for example, retrieving the result, and then doing consensus with whatever has been running in the meantime on Bon in a Box. Bon in a Box can run everywhere. It could run on your computer, on a server. We can host it, but you can host it as well. It's Dockerized. It runs on my home computer here, on my office computer, and we have a server also running it. Galaxy for Ecology runs on the Galaxy supercomputer networks, and they have already a few EBV models. So it's just an example to show that this is theoretically possible to just call an API, retrieve the result, and work from it. Now, the next slide might be the only thing you remember in 1 year. I don't know, I made it really big and strong. Interoperability is freedom within. So some people might see interoperability as a big set of constraints, something that blocks you from doing whatever you want. It might be true for the outside of the box, but inside the box, as long as what you received was standard and intelligible, and you output something that's standard and intelligible for the next step, then in the middle, you can just do whatever you want. Well, as long as it's scientifically valid, of course, but still. So it actually adds some freedom to do whatever you want inside the step, knowing it can be reused everywhere. There is a little constraint I would add. Imagine this is a Bon in a Box step. This is the step before, the step after. When it comes in, if you know this will be used in an interoperability context, you can't just do like you would do when running scripts for your regular research, where you just assess the results as you go, you look at the data, is it good? Okay, then I run the next thing, because you don't know what's going to come in. You're not actually looking at the steps along the way. So there needs to be a little validation here that the input makes sense before you try running whatever you're doing, or else you might be running on some input that is completely bad. So in the arrow here, there's a little validation that needs to be done. And if you don't want to fool the next step, there should be a little validation here also to stamp if there's an error or a warning, or if it looks okay. In Bon in a Box, you can output an error and it will just halt the whole pipeline for the person running it to actually look what's going on. For example, you're trying to cross-validate something, and there's so much variation between them, it looks like it's completely random. Well, maybe you should halt the pipeline there. So this is a fundamental principle of the pipeline engine, because it allows the labs to collaborate together in the same pipeline, which is something that was really hard before. In Quebec here, we had this lab that wants to work only in Julia, this lab that wants to work only in R, and now it's possible to actually do both. And we were calling a planetary computer API, and that works with Python. Why not? It just, at the end, you click run, and it aligns the 3 languages and works. So in our context, it allowed for several benefits. The different environment, what I just explained, since we communicate to inputs and outputs, syntactic interoperability, we can fix that. It's hard to audit the results because, often only the final result is shown, and you have to kind of look at the details of the paper, but even then, it's not always easy to see every step of what happened. So using the fact that every step has intelligible outputs that should be documented appropriately, then you can look at all these outputs and see and validate each of them. And so the results being visible is like a byproduct of interoperability, but it actually adds transparency and trust. And the documentation in code is public, just to reinforce that. And the scattering of resources is also a problem. We have really nice standard data. Remember that BON-in-a-Box is not a data repository. It's a model repository and a model running tool. And it feeds on data that is on GBIF, on a stack catalog, but also local data. How do you get all this together? So this is where semantic interoperability would be really an asset. What we need to do right now in our context is that, let's say you have standard data coming from somewhere, standard like GBIF, and you have observation data that is not standard. You have to write some code, a code block, put it in the pipeline in between the data and the model, just to make it standard so that the data receives standard data from both sources that can be compiled together. This works, but it requires the person who wants to use non-standard data to actually go and code something. While if we have semantic interoperability, then we'd expect that the non-standard data can be understood by the AI and actually standardized or used. This is a weakness we have right now, but as you know, semantic interoperability is still a field of research. Now, I've went over interoperability. I'm just going to mention the other founding principles we had for the pipeline engine. It's open source, code, and platform, fully transparent. We want the pipelines to be generalizable. So we don't want a pipeline that works only for the moose in Quebec. We want pipeline that works for all large animals, large mammals with wide territories, for example, that would work with the deer or somewhere else, or we want the pipelines to be reproducible. So let's say you have a pipeline that calculates the species distribution models, new observations come in, you change the date for 2025, and then you click run, you get your new results. And that could even be done automatically. So this is reproducibility, reusable. So a single script can be reused in many pipelines, or a pipeline can even be used in the context of another pipeline as a sub-step. And transparency, so that all intermediate results are visible, source code, references, so that it's easy to, actually transparency also supports reproducibility. So these are the other founding principles we had for the pipeline engine. So that's it for my presentation. I think we can now, Nuria, go for the questions.
Yeah, thank you so much, Jean-Michel. Yes, we can now address the questions. I think that the ones in the Q&A, only Flavio and you can check it, because you are the co-host and host, right? Because for me, I think it's empty.
Yeah, it's empty for me as well. So I don't see any questions in the Q&A.
Okay, so if someone wants to raise their hand and ask directly also, and open the microphone, just go ahead. Okay, no questions for now. But oh yeah, Ken.
Well, I'll just make a quick reaction. Which, first of all, love the follow-up, Flavio and Jean-Michel, and especially Jean-Michel. I wanted to get to your point about this freedom within idea. I haven't seen that, and I think it's a really, really important point. So that's a nice way to frame this and to try to convey it. I think it's valuable, and one of the things we could be doing better is developing the tools that make the two ends of that as easy as possible for scientists. I hinted at that, but I think I think bringing that together with the ideas you presented, we need to make that just a standard part of science and something people don't see as a burden. We all know how much people like writing metadata, right? So you know, how do how do we make it accessible and something people just do?
Mm-hmm. Yeah, and what I found was really hard also is the validation of the inputs. So it's something that in computer science, I come from a computer science background, software engineering, and it's something that has been discussed and published like a whole lot, because we live in a world where the inputs are totally uncertain, because they come from users, because they come from unclean data or the big data, which is fundamentally chaotic. So this validation has been published on a lot, and there's a culture of it, and even then it's still difficult. So this is really something also in the scientific world where we're used to a more linear flow where you know your stuff all along the way. There's a shift of culture to say, hey, this step I'm writing can receive just about anything that could be wrong. It's a shift in culture. And the tools, there must be development of thought of tools and methods to make it easier. Like
yeah, we didn't talk about provenance much, but that's an important step here, making sure that it's not garbage in, garbage out, right? That it's transparent. You know what the inputs are when you're relying not just on your science, but on the rest of the world's as well. So, I think we need that. And we've talked about a variety of ways to grade or score models and data for their appropriateness for a particular application or particular time and place. Ranging from, from the metadata itself, accuracy assessments, to even eventually crowdsourcing things. If we had a large ecosystem of people using it, can we give 1 to 5 stars and make it like restaurant reviews? If hundreds of scientists endorse and use these data, that's maybe not the only thing, but that gives you more confidence if you have a 4.5 star review over a 1.5 star review.
Yeah.
I also wonder, Ken or Jean-Michel, I don't know how much experience you have with it, but there's other systems like climate change research and so on, where they already are probably a few steps down the line compared to ecosystem services or biodiversity. And I wonder how much we might be able to engage and learn from them, or learn from how they got to where they're at.
I would point to climate change there, and the IPCC in particular, as a force that helped standardize climate assessments. But because of course we know, especially with the global climate system, that one model isn't correct, and there was this need to produce common scenarios and run and test climate models. And IPBES has tried to do a similar thing, except the biodiversity and ecosystem service models are way more complex and heterogeneous than a global climate model. So I think there's indeed a lot to be learned from the climate community. Some of the semantic principles that I flashed on that one slide about how we develop good descriptors for data and model elements have their roots in the climate community for describing variables. So yeah, I think that's a good and helpful point.
I would say the same. And Andy had pointed me towards this OS Climate initiative, for example, built by the people who built Linux. So the climate is many steps ahead, yes, and we have a more complex challenge as well.
Yeah, thank you. I want to just make a quick comment about what you were talking about, and is that we were doing a review of ecosystem services literature, and I was a little bit surprised because some papers doesn't define the ecosystem service. I mean, they just say like some of them, right? Like we are assessing assistance, future, things like this, like a little bit vague. And just the name, and I was like, even without the definition, like a clear definition, you don't know exactly what they are assessing, right? And this is so important for interoperability, for the semantic part is so critical, right? Andre, raise a hand.
Hello. Good morning to you. We are on the Las Palmas de Gran Canaria in Spain. And I would like to say that we are working on the one project, which is project on maritime special planning, where we're actually dealing with also ecosystem services. And idea is to develop the tool that can assess number of the ecosystem services within the waters of the European seas. And we are using the interoperability of the habitat distribution, benthic habitat distribution, which is using the standard. And this is the European standard for the UNIS. So using this standard, we are able to identify what are the services, and then we can actually superpose within the maritime special plans that are again using another standard for the presenting the plans, and we can understand what is the impact of the plans for the maritime special plans and the services. So it's practically, I really like your presentation. They are all fantastic one. We really enjoy it, and we see lots of things that you are developing. And we see also that we are somehow in the good directions. And we just wanted to notice that we have some work done and that we are actually using this interoperability for developing our models and the results.
Yeah, great points. Just to respond to that, I didn't talk about this, but if you take a moment and imagine a world without the periodic table or Linnaean taxonomy, and imagine trying to do chemistry or biology without those things, and what a horrible mess that would be. And UNIS is an example of habitat type classification, as you said. So good, that there are standards out there, that you're using them. Those are important. And if we were all off doing our own things, that you could see very quickly how messy they would get. I've thought a little bit about like how these standards evolved in multiple stages. So you had a first stage where you might have a research team that's say in multiple countries, and they need to make sure that the data they're collecting is consistent. So you might just have some internal data glossaries that are the same, and data collection procedures. And you can see how that's obviously needed. You had a second stage of metadata for when we started putting data on the web, and other users had to be able to interpret it and understand what it was. And this third stage that I was talking about and proposing with semantic interoperability is about going to a third stage of making them interpretable by machines as well as humans, and making sure that that's consistent. So that's maybe another way of thinking about this broader path towards standards, and sort of a Tower of Babel problem if you want to get deep into human history and mythology.
Well, thank you so much. Unfortunately, we are running out of time, but thank you very much to everybody for attending the webinar. Thank you especially to Ken, Jean-Michel, Flavio for being here and giving these super nice talks. And see you soon.